Yes, dear students, today we shall discuss about how to produce frequency modulated wave. The frequency modulated wave is obtained by varying the amplitude of the carrier signal, keeping constant phase angle of the carrier signal is constant, whereas the frequency of the carrier signal is varied in accordance with the amplitude of the modulating signal. As a result, the frequency modulated wave is obtained. And you know it very well. Suppose this is a message signal which is to be conveyed or transmitted from one point to another point, and you require modulations. That is, you have to take very high carrier frequency such that in frequency modulations, the frequency of this, I will call it as FC, this is varied in accordance with the amplitude of this message signal. Now, how it is generated? So, we have studied the graphical method of representing this message or modulating signal and carrier signal, and after modulation you get a frequency modulated wave. Now let us study how it can be generated using a transistor. Usually there are two types of transistors, that is, this is an NPN transistor. We can use this transistor to generate FM generation. But in this case, if you take a forward characteristics, that is the collector current against the collector emitter voltage. See this, from year to year up to this it almost constant, but not exactly constant. Therefore, for this range of collector emitter output voltage, the current is not exactly constant, it varies slowly. That means there is a change in current. Therefore, if I take this as a message signal, the current should vary according to the message signal. Because of this, there is no perfect variation of IC. This produces distortion in the frequency modulated wave. Therefore, instead of using this bipolar junction transistor, we will use FET. This is symbolic representation of FET. There are two FETs, N-channel FET and P-channel FET. If the arrow mark at this is outside, you call it as N-channel FET. The three terminals of junction transistor is named as emitter, base and collector. Whereas here we represent this as source. Emitter and source are the same. Here source means it gives a free electrons as a source. And this is called gate. It acts a function like base of the transistor. It acts as an open gate or closed gate for the flow of electronic charges from source to this point. This is called drain. Drain means ಎಳೆಯೋದು. So the current is drained. Drained ಅಂದರೆ ಮುಳುಗೋದಕ್ಕೂ ಎಳೆಯೋದು. The drained from the source. How much the drain current flows, it depends upon the gate voltage. How much gate is opened, whether it is fully opened or fully closed or halfly opened, like that. The drain current depends. But the characteristics of this, output characteristics of this FET is like this. Instead of collector current, I will represent this as drain current. Instead of collector emitter voltage, I will consider this as drain and source voltage. Then if you plot a graph, you will get like this. That means the drain current remains constant for a certain length of drain voltage. That is, drain current is independent of the applied voltage between the drain and source. Since drain is independent, that means drain remains constant, and this transistor is preferred in producing frequency modulation, and there is no much distortions are produced in frequency modulation or frequency generation, frequency modulated wave generation, if we use a transistor. Therefore, now we shall discuss about FET, field effect transistor, reactance modulator. This field effect transistor reactance modulator is used to produce frequency modulated wave, FM wave. Now, I will draw a circuit so that it can generate frequency modulated wave. I will draw the FET circuit. This is a field effect transistor, N-channel field effect transistor. This is source, this is gate, and this is drain. This is output, and to the input gate I will connect a capacitor here of capacitance C and a resistor of resistance R. This is a simple circuit which will generate the frequency modulated wave. In frequency modulated wave, the frequency of the carrier wave is varied in accordance with the message signal or modulating signal. Now let us apply the voltage between gate and source. I will call this as gate source voltage. This gate source voltage is our message signal. So it will be like this. This AC voltage is applied here of low frequency. Therefore, it is message signal. Here, gate source voltage means message signal. The message signal is represented as E is equal to EM. E is equal to EM sin of omega mt. Instead of E, since this E is applied between gate and source, I will call this as VGS, gate source voltage. Now, let us look the total impedance. What is the difference between resistance and impedance? Both are same. Resistance is stopping power for the current. Resist for the flow of current. Similarly, impedance means resist the flow of current. But resistance resists the flow of both AC and DC, whereas impedance resists the flow of AC. Therefore, instead of calling resistance, I will call impedance, where it resists the flow of AC. Since this is an AC signal, you will get a AC signal output here. And the resistance offered for that AC between these two terminals, I will call this as Z, the impedance. I will consider this point as A and B. So, Z is the impedance looking towards this circuit from the point A and B. ಹಿಂಗೆ ನೋಡಿದಾಗ ಅದ್ರ ನೆಟ್ ಇಂಪಿಡೆನ್ಸ್ Z ಇಲ್ಲಿ. What is the impedance of R? R itself. What is the impedance of C? We call it as reactance, that is Xc. So you should know that the impedance of resistor is R itself. The impedance of capacitor is Xc, which is denoted by 1 by omega C, which is equal to 1 over, where omega is nothing but 2 pi f into C. This is the reactance or opposition offered for the AC by capacitor. If you use an inductance, we call the opposition offered by the inductance as XL, which is given by omega L, which is equal to 2 pi FL. This is the opposition offered for AC by the inductor. R is for resistance, X is called capacitive reactance, XL is called inductive reactance. All these will oppose the flow of current, whatever it may be. Now, the resistance or reactance, it is also called impedance. The reactance, the net impedances. Impedance means the net values of all the resistance of the circuit. Here the reactance is Xc. The reactance of this R is R itself. Therefore, the effective value of this opposition is called impedance Z. To calculate this Z, let us consider a voltage V. Let a voltage V be applied to this transistor between the point A and B. When the voltage is applied, let ID is the drain current flows through the drain. And by this voltage, let IG is the gate current flows. Here the current flows through this is IG. The message signal is applied between gate and source, that is VGS. To calculate the impedance Z looking from A and B towards the circuit, we will apply a voltage V between these 2 points A and B. Now, what is drain current? So, drain current is given by the drain voltage into drain resistance. Leave it, we don't. What is IG? It is the current flowing through C and R. Okay, and from here to here, the applied voltage is V. Therefore, the gate current IG is equal to, what is the net reactance? Applied voltage divided by net resistance. Voltage by resistance is current. Therefore, the gate current flowing through this is voltage between these 2 points, that is our applied voltage V, divided by resistance, total resistance. Or, since these two are in series, I will write this R plus Xc by J. Or we can write this as V divided by R minus Jxc. You just remind that why we are taking Z. You should know this AC analysis, but I will not explain this. This is positive X direction. R is the resistance offered. This is negative Y axis, whereas J is the direction, minus J is the direction. And this is the capacitive reactance along negative X axis. And this is XL, inductive reactance along positive Y axis. And we will represent this as plus J. Therefore, resistance offered by the resistor for AC is R itself. Resistance offered by the capacitor for AC is minus Jxc. Similarly, resistance offered by the inductor for AC is plus Jxc, Jxl. Here, the resistance offered by the capacitance is minus Jxc. Resistance offered by R is R itself. From Ohm's law, I is equal to V by R. V divided by net resistance R plus minus Jxc. R1 plus R2 ತರ. ಇದು ನೆಗೆಟಿವ್ ಆದ್ದರಿಂದ R minus Jxc. This is the gate current flows through this. Now, when gate current flows, what is the gate source voltage? Now I will apply gate source voltage, that is message signal between gate and source. So now gate source voltage is, the voltage between these two is current Ig flows through R into resistance R. Therefore, current Ig into resistance R. But what is Ig from this equation? This is V over R minus Jxc is our Ig into R. So, current flows through R is Ig, voltage is Vgs. From Ohm's law, voltage Vgs is equal to current into resistance. Current into resistance. This is another expression. Now, calculate this. Keeping this in mind, for gate source voltage, this is electric field, it converts into the output current Id. Therefore, it is called field effect transistor. That is, bipolar transistor is a current device. The input base current produces output collector current there. Here the input gate source voltage, input voltage produces output current. Therefore, it is called field effect transistor. And we know that the transconductance denoted by Gm. Transconductance, input voltage is transferred to the output as a current. This is called transconductance denoted by Gm. Conductance is nothing but reciprocal of resistance. Resistance and the resist manutte. Conductance and conduct manutte. Therefore, conductance is inversely proportional to resistance. Unit of resistance is ohm. Unit of conductance is mho. Therefore, from Ohm's law, resistance is V by I, voltage by current. Since conductance is reciprocal of resistance, conductance is current divided by voltage. Therefore, for FET we write that conductance as Gm. That is called transconductance. Conductance means current divided by voltage. I will write transconductance means input voltage is transferred to the output current. Therefore, it is defined as output current divided by input voltage. Or the drain current Id is equal to Gm into Vgs. But what is Vgs? Vgs is equal to V divided by R minus Jxc into R. I will substitute here. Id is equal to Gm into Vgs is, once you see, Vgs is V by R minus Jxc into R. V divided by R minus Jxc into R. That is Vgs. Now, I will simplify this. V divided by I, this is Id, okay? Let it goes upward and it comes downward. V by Id from this expression. V by Id is equal to, R minus Jxc divided by Gm into R. Your capital V is the output voltage we applied. Because in order to calculate impedance, you should need both voltage and current. Id is the current, V is the output voltage. Therefore, output impedance Z is equal to voltage by current. Therefore, output voltage divided by output current is output impedance Z looking through AB, which is equal to, I will write 1 by Gm like this, R minus Jxc by R by R is 1, minus Jxc divided by R. Here usually in this circuit you will consider capacitive reactance Xc is made very much greater than R. This is why, because see, F is equal, sorry, Xc is equal to 1 over omega c, 1 over 2 pi, and F is the frequency of modulating signal, it's very low, but C is in terms of microfarad. Whatever may be this value, in terms of microfarad means -6. When it goes up, it becomes +6, means crore. Therefore, compared to this, one can be neglected. This is 10 power 6 times. This 1, so you can neglect. Compared to 1 crore, one can be neglected. Therefore, since X is very much greater than R, one can be neglected. In that case, the impedance Z is equal to 1 by Gm into minus Jxc divided by. Now, if I take only the magnitude instead of direction, that is negative x-axis is the capacitive reactance. Negative y-axis is capacitive reactance. Positive y-axis is inductive reactance. X-axis is resistance. That is the direction. Okay. So if you take the magnitude only, minus j becomes 1. That is only magnitude. We won't consider the direction. J represents direction. Minus j represents negative y-axis. Plus j represents positive y-axis. Therefore, if you take only the magnitude, you will get Xc by Gm into R. But what is Xc? Capacitive reactance is given by 1 over omega c into Gm into R. But we know that omega is angular frequency, which is 2 pi f, where f is the frequency of the message signal, modulating signal applied between gate and source. C into Gm into R. Consider this C into Gm into R. C into Gm into R. What is the unit of this? C is in terms of farad. Gm, that is mho. Conductance. Resistance is ohm. Mho and ohm are opposite to each other, they get cancelled. Therefore, the entire, even it contains Gm and R, the entire product has a unit of capacitance, farad, capacitance. Therefore, the entire can be written as Z is equal to 1 over 2 pi f into C equivalent. I will simply write this as C equivalent because entire unit of this is capacitive capacitance. That is farad. Therefore, where compared to this, where C equivalent is Gm into Rc. So instead of writing Gm Rc, simply I will write C equivalent. Okay, that is Z is equal to 1 over 2 pi is 1 omega into C equivalent. Therefore, this is X C equivalent because Xc is 1 over omega c. Here you get 1 over omega c equivalent. Therefore, it is Xc equivalent. Thus, the input impedance looking towards this is a capacitive reactance. X equivalent is capacitive reactance. Suppose if instead of connecting C, if you connect L, inductance, then the impedance looking towards this is inductive reactance. Therefore, we get impedance between the point A and B, either capacitive reactance or inductive reactance. That is either the value of capacitance or value of inductance, depending upon the component connected here. If you connect C, capacitive reactance. If you connect L, impedance, that is inductive reactance. Now, this between A and B is inductive reactance. Now here it is capacitive reactance. See, now it is capacitive reactance. XCEQ, where XCEQ is our 1 over omega CEQ. C equivalent and the equivalent C, where C equivalent is GM into RC. Output is capacitive reactance. That is our impedance Z. Now, you see this circuit. I will consider this point A and B. And to the left there is a FET reactance modulator where C is connected to the gate. Then what is the reactance here? Z is capacitive reactance. Therefore, I will write this as C equivalent. You know what is C equivalent, which is given by GMRC. Now, if I connect a tank circuit here, so I will connect C and L. What is you mean by tank circuit? Tank circuit is the parallel combination of L and C is called tank circuit. In the tank circuit, if the voltage is applied, current produced in the tank circuit is maximum only for a particular frequency. So if V is the applied voltage here and current flows in the tank circuit, if you plot a graph of voltage against current, this increases and again decreases. For a particular value, only the current in the circuit is maximum. This is XC less than, this is greater than XL. At this point, where the current in the circuit is maximum, it is XC is equal to XL. Low current below this voltage. This is for capacitive reactance. Again, see, the current is less. Above this V, again the current is less. That is by inductive reactance. But only at the particular value of V, where the current of the tank circuit is maximum because of the supplied voltage, current flows in the tank circuit, it is maximum. Yavaga, when reactance of this is equal to reactance of this. At this point, it is XC is equal to XL. Here, XC less than XL. Here, XL greater than XC. At this point, it is XL equals XC. This point or this is called resonant frequency. The resonant in the circuit is that if the current flows in the tank circuit is maximum, we call it as a resonant current. At resonant current, at maximum current, XC is equal to XL. What is XC? It is omega C. What is XL? It is omega L. Or simply I can write this as omega squared is equal to 1 by LC. XC equals XL at resonance. XC means 1 over omega C, which is equal to XL is omega L. Therefore, on cross multiplying simplifying omega into omega squared equals 1 by LC. Or simply omega is equal to 1 over root LC. But omega is 2 pi f. 2 pi f equals 1 by root LC. Therefore, frequency f is equal to 1 over 2 pi root LC. You just remember this. You need not to derive this. Any tank circuit, a tank circuit consists of parallel combination of L and C, where the frequency of this tank circuit is given by f is equal to 1 over 2 pi root LC. Okay. The frequency produced by this tank circuit is called carrier frequency. Carrier frequency. That is, I will write this as FC. Whereas frequency applied to the gate source voltage, that is VGS, message signal, frequency is FM. Here the C equivalent depends upon, how do C equivalent depends? The output is a capacitive reactance. This capacitive reactance depends upon the drain current. The drain current depends upon the input voltage applied here. That is message signal. Therefore, this totally we can say that reactance of this is directly proportional to message signal applied between gate and source. You see, if that reactance is applied to a tank circuit, if this is C, here is C, here is C, parallel combination, net capacitance C plus C equivalent. Therefore, frequency of this model carrier wave now becomes F is equal to 1 over 2 pi square root of L plus, instead of C, C equivalent is also applied here. This is C plus C equivalent. C equivalent changes. F equals 1 over 2 pi square root of L plus net. C equivalent, C are in parallel. Net value is C plus C equivalent. When C equivalent changes, frequency also changes. That is, when message signal is 0, here, when message signal VGS is 0, there is no gate source voltage, there is no drain current, therefore there is no capacitive reactance here. C equivalent is 0. Therefore, from this expression, we can say that F equals 1 over 2 pi root L into C plus C equivalent is 0. Therefore, it is F is equal to 1 over 2 pi root LC. That is carrier frequency. So there is no change in carrier frequency. But during this positive cycle, VGS increases. Therefore, ID changes according to this increase in the voltage. C equivalent also changes. When C equivalent changes, F equals 1 over 2 pi root of L into C plus C equivalent. From this expression, C equivalent changes, the ratio changes, that is frequency also changes. Therefore, we can say that the frequency F of the tank circuit, output of the tank circuit, changes in accordance with the voltage applied between these two, that is message signal. This is our frequency modulated wave. However, in frequency modulated wave, we have taken that Xc is very much greater than R. This is because of C, Xc is 1 over omega C. C is in terms of microfarad goes, it plus, that is 1 crore you will get. R is only 10k, or 10 power 4. Therefore, compared to 1 crore, this R can be neglected. Therefore, we have considered the case Xc is very much greater than. How much it should be greater? Not much greater. There is a rule that Xc is equal to N times R. How much N? N varies between 5 to 10. Xc is equal to 5R or Xc is equal to 10R. Between 5 to 10R, N changes. So, N values may be between 5 to 10. You have to select Xc such that it should be equal to NR. What is Xc? Xc is 1 over omega C, which is equal to N into R. R 1 over omega is 2 pi F into C is equal to N into R. Now, we know that Gm RC is equal to C equivalent. From this expression, C equals C equivalent divided by GMR. Substitute this in this equation. You get 1 over 2 pi F into, where C is C equivalent divided by GMR equals NR. When it goes up, we get GMR divided by 2 pi FC equivalent equals NR. RR get cancelled. Therefore, finally, C equivalent is equal to cross multiplication GM divided by 2 pi N. This is used for solving the problem. So Gm R divided by 2 pi Fn C equivalent is equal to Nr. R get cancelled, and you get C equivalent is equal to Gm divided by N ikkada varutte Gm over 2 pi Fn F. This formula is used for some problems. Thank you. Next week we shall discuss about the problems on frequency modulation and problems on FET reactance tube modulator. Thank you very much.